Ja, dann machen wir es auf Englisch. Dankeschön.
Prima, vielen Dank. Sie bekommen von mir ein paar Worte auf Deutsch und dann sind alle, die auch etwas auf Deutsch hören wollen, vielleicht zufriedengestellt. Vielen Dank für die Einladung. Ich habe das sehr gerne angenommen und bin auch ausdrücklich von der Ministerin, Frau Professor Johanna Wanka, gebeten worden, Ihnen allen diese Grüße zu übermitteln. Wir fördern diese Veranstaltung auch sehr gerne. Es ist für uns eine Premiere. Wir nehmen das erste Mal teil an der publica. Wir betreten sozusagen Neuland, um dieses ja schon mehrfach benutzte und diskutierte Wort hier auch einmal einzuführen und dann auch noch gleich auf eine Konferenz, die den Titel hat Into the Wild. Wenn wir dann noch bedenken, dass die Digitalisierung in der Wirtschaft zurzeit als neue industrielle Revolution bezeichnet wird, dann ist mit Neuland, Wildheit oder Wildnis und Revolution sind das alles ziemlich mutige Begriffe für eine Einrichtung wie ein Ministerium, das normalerweise mit vielen traditionellen Bs arbeitet. Bundesregierung, Beamten, Behörden, Bürokratie und jetzt also Neuland, Wildnis, Revolution. Ich möchte Ihnen deswegen auch keine klugen Bemerkungen hier vorstellen zur Digitalisierung, zum Netz oder zu Social Media. Das kennen Sie als Fachpublikum mindestens genauso gut und im Zweifelsfall auch besser als ich. Ich will Ihnen aber kurz erklären, warum uns das Thema so am Herzen liegt. Das hat zum einen einen relativ einfachen Hintergrund. Die Bundesregierung richtet seit langer Zeit jedes Jahr ein Wissenschaftsjahr aus. Und oh Wunder, dieses Jahr steht das Thema unter dem Motto die digitale Gesellschaft. Jetzt werden Sie vielleicht sagen, naja, es ist auch nicht so schwierig, sich da drauf zu setzen. Sie sollten aber wissen, dass diese Themen auch lange vor dem ganzen Diskussion um Edward Snowden und dass die Beschleunigung dieses Themas im letzten Sommer gefunden worden sind. Es ist also schon auch ein bisschen Vorausschau des Bundesministeriums für Bildung und Forschung dabei gewesen, als wir dieses Thema für dieses Jahr ausgewählt haben. Wir machen im Übrigen auch relativ elaborierte Foresight-Prozesse zur technologischen und gesellschaftlichen Erneuerung, die erst am Horizont so aufscheinen, um gewappnet zu sein, was da kommen könnte. Das Wissenschaftsjahr hat zum Ziel, erst einmal die Bürger für die Themen der Wissenschaft und für das wissenschaftliche Arbeiten und Denken als solches zu begeistern, zu interessieren, die Öffentlichkeit anzuregen, dazu berichten, auch natürlich das Gespräch der Experten untereinander zu fördern. Und das ist dann ein Auftrag an alle drei, diejenigen, die das organisieren, die politischen Institutionen, aber genauso wie die Bürger. Da gilt der Grundsatz, informiert euch. Und es ist auch immer eine Herausforderung an Wissenschaftler und Experten, erklärt euch und erklärt euch verständlich. Wir haben dazu auch einen Stand hier, den Sie drüben weiter sehen können. Ich lade Sie natürlich alle sehr herzlich ein, dass Sie den Stand des Wissenschaftsjahres besuchen und dort etwas an den Aktivitäten teilnehmen können. Mit ein bisschen, einer kleinen Aufwand, einem kleinen Posting, gibt es dort auch Hackerbrause umsonst zu trinken. Das BMBF ist aus einem zweiten Grunde besonders an diesem Thema interessiert. Wir sind ja sozusagen diejenigen, die sich zuvorderst um die guten Rahmenbedingungen für Wissenschaft und Forschung zu sorgen haben. Und das ist dann nicht nur in unserem Denken, in unserer Arbeit eine Erlaubnis zu Neugier, sondern eigentlich geradezu eine Aufforderung zu Neugier. Also alles, was mit Laboratorien zu tun hat, mit Ausprobieren, mit Versuchen, auch mit Irrtum, wenn daraus jedenfalls dann auch Umkehr folgt, sind das Dinge, die uns nicht fremd sind, sondern die für uns gewünscht sind. Wir haben viel mit der Pluralität unter den Akteuren der Wissenschaft und der Forschung zu tun. Die vertragen wenig Hierarchie. Das ist auch etwas, was normalerweise im Regierungshandeln ganz anders daherkommt, aber ich glaube, hierher gut passt. Und Wissenschaft und Forschung basieren elementar auf Offenheit und Austausch, auf interdisziplinärem Austausch. Und genau das ist auch einer der entscheidenden Gründe, warum wir finden, dass Veranstaltungen wie diese hier gefördert gehören. Die Stichworte Open Access und Open Data, jetzt kürzlich gerade verstärkt auch das Thema Citizen Science, sind einige Dinge, die Schwerpunkte für unsere Arbeit sind. Und der dritte entscheidende Punkt ist, der ist vielleicht noch etwas größer. Das ist der Punkt, dass uns das ganze Thema Innovation, man kann auch sagen Erneuerungsfähigkeit einer Gesellschaft am Herzen liegt. Und das verstehen wir bewusst nicht nur technologisch, sondern genauso gut gesellschaftlich, weil unserer Ansicht nach davon überhaupt entscheidend abhängt die Zukunftsfähigkeit einer Gesellschaft. Nicht, ob sie besonders reich ist, ob sie besonders mächtig ist, ob sie im Mittelpunkt des Weltgeschehens oder in irgendeiner ruhigen Nische stattfindet, sondern wie innovativ sie ist. Also all die Fragen, was auf uns Neues technologisch zukommt, genauso wie das, aber auch, was die Digitalisierung mit den Menschen macht, den Errungenschaften, den Sorgen, den Hoffnungen, den Nöten, der Skepsis, das interessiert uns. Wir haben aber auch eine Bitte, einen Punkt, der uns immer sehr wichtig ist bei all diesen Diskussionen, wenn wir uns auch von einigen wissenschaftlich-ethischen Standards leiten lassen. Die bedeuten, am Ende, um Erkenntnisgewinn zu haben, braucht es auch ein Stück vernunftgeleitete Debatte. Es sollte empirischer Überprüfbarkeit dann und wann schon standhalten. Gefühle sind erlaubt, auch geboten, aber sie sollten wissensrückgekoppelt sein. Sonst kommen wir gemeinsam bei Erkenntnis über die Dinge, die kommen werden und wie man sie am besten organisiert, nicht weiter. Ich bin sehr beeindruckt von der Vielzahl der Themen, die hier sind. Wir wollen und müssen als Bundesregierung, als Politik lernfähig sein und dürfen selber natürlich die Neugier auch nicht verlernen. Deswegen finden wir eine Gesamtveranstaltung wie diese auch sehr interessant, um zu hören, was geändert werden muss, wo auch vielleicht Politik Freiräume schaffen muss oder mehr Schutz bieten muss. Sie hören da schon ein bisschen raus, bei noch so viel Wildheit und noch so viel Neuland, ganz ohne Regeln geht es meistens dann doch nicht. Die Frage ist ein bisschen, wer macht sie? Muss das immer gleich von oben nach unten gehen? Gibt es nicht auch viel Möglichkeiten der Selbstorganisation? Ich glaube, das ist eine der bemerkenswertesten Eigenschaften gerade der Digitalisierung, dass die Möglichkeiten zur Selbstorganisation viel stärker gegeben sind und ja auch genutzt werden. Aber bei allen Dingen, die rings sich auch um Schutz der Privatheit drehen, das ist nicht nur eine private Angelegenheit, das bleibt ganz am Ende auch eine öffentliche Angelegenheit, eine politische Angelegenheit. Und deswegen finde ich es sehr gut, dass der Kongress insgesamt schon seit Jahren unter dem Titel Republica, also von den öffentlichen Dingen steht. Sie werden ja gleich einen Vortrag zum Quantencomputer hören. Soweit ich das richtig verstanden habe, physikalisch gesehen, ist das bereits ein Schritt über die klassische Digitalisierung hinaus. Und wenn das, was da theoretisch versprochen wird, sich auch praktisch einlösen lässt, dann wird das auch wahrscheinlich ziemliche Folgen haben, zum Beispiel für die Fähigkeit, sichere Verschlüsselung noch in Gang zu setzen, weil dann da Kompetenzen und Fähigkeiten entstehen, die das ganze Thema Schutz und Verschlüsselung noch einmal eine ganze Ecke schwieriger machen. Und deswegen ist es gut, wenn wir uns erinnern, vor 30 Jahren, ungefähr 30 Jahren, als dieser berühmte Film von Stanley Kubrick, Odyssee im Weltraum, rausgekommen ist, mit dem Bordcomputer HAL, diesem großen, roten, blinkenden Auge damals und diesen sehr freundlichen, netten Begrüßungen für den Anwender, der antwortet auf den Vorhalt, dass das, was er da an Fehlern an der Antennenanlage des Raumschiffes gemessen hat, dass das nicht stimmig sei, sagt er, Computer meiner Serie haben noch niemals Fehler gemacht, es muss an den Menschen liegen. Und das, glaube ich, ist auch der entscheidende Punkt, wenn wir uns über Quantencomputer, deren Anwendbarkeit und all das Weitere, was hier ein Thema spielt, vor Augen halten. Es hängt letztendlich immer an uns selber, an den Menschen. Und in diesem Sinne finde ich das prima, dass Sie hier untereinander diskutieren, dass wir einen kleinen Teil dazu beitragen können, dass das hier in dem Rahmen stattfinden kann, und wünsche Ihnen viele und gute Diskussionen und vor allen Dingen jetzt viel Spaß und Anregungen durch den folgenden Vortrag. Vielen Dank.
Ja, vielen Dank für diese einleitenden Worte. Let's get back to English now. Our next speaker, he works at the Nano Energy Technology Center at the University Duisburg, Essen. He believes in science and education and wants to bring science to the masses, what he actually does by streaming his own podcast, Methodisch Inkorrekt. Please give a big hand to Nicolas Wöhrl, and his diamonds are quantum computers' best friend.
Thank you very much. You guys really surprised me a bit. There is a presentation without any hashtag, any buzzword. Actually, I'm stating that I'm talking about quantum mechanics, quantum computers, and you're still here. Thank you very much for that. I'm a physicist. Even more, I'm a material scientist. I'm very fascinated by materials, and that for good reasons, because looking back at human history, you see that materials always defined how people lived. Actually, materials gave whole time eras their names, like the Stone Age. People used stones as weapons, as tools. A little later, they used bronze, a metal, and a metal alloy as a material with harder properties, so they had an advantage using this material. Even later, there was this iron era, a metal which is even harder. So again, a technological advantage by using better materials. So materials always gave an advantage for people. Not only materials, actually, but also the technology that arises from these materials. If you're looking at the last few hundred years, there was this classical age, the Roman Empire, they had some technology that they used very efficiently, or the age of discovery, where navigational skills made the difference of who had the power in the world. And looking back at the last few decades, it was this technology which pretty much defined how the power was distributed in our world, dividing the world into East and West. And this power was so big that even established scientists like Professor Einstein said this year, "I do not know how the Third World War will be fought, but I can tell you what they will use in the fourth, rocks again." So another Stone Age. So the question is, what comes next? What is the next weapon? And I guess by now we can help Professor Einstein a little bit here. The next weapon will be this here. Well, not really a sword from the game Minecraft, but it's directing us in the right direction, because if you're thinking about the next weapon, the next technology that will change the shape of the world or the power distribution, it makes sense to think about what is it what will be important in the next few decades. What is it what we are fighting for? And we believe that will be information, that will be knowledge, that will be crucial that we participate in that game, gaining knowledge and information. So the 21st century trenches will be this year, computer chips. Whoever will have the faster processors, the better algorithms, whoever has this technology will have an advantage in this world. So my talk today will be, I want to show you that we are not so much in a time of an evolution of this technology, but a time of a revolution. We will talk about why quantum computers might play a role in this revolution. I want to show you, and we are actually building here a quantum computer, and I will show you why diamonds will have a role in this development. So whenever we are looking into the future, it makes first sense to look a little bit back on the past of computer technology. And whenever we are talking about the past of computer technology, we are looking at this here, Moore's Law. Where are we coming from? And Moore's Law is Gordon Moore was a engineer in 1965. That's pretty remarkable. 1965, in the early days of computer technology, he stated that the processors will develop like this line is showing here, that we see a doubling of transistors on our processors every 2 years. This is what the line says, and the dots, the data points are what actually happened. So the prediction was pretty good from him. And what's really remarkable is if you look here at the y-axis, that we started with a few thousand transistors, and now we're in the billions of transistors on a single chip. How was that possible? Well, by a simple idea, we're just making the transistor smaller. That's really plain idea. If you look at the sizes of a single transistor on such a computer chip, you see that we started with fairly large transistors, like 10 micrometers large, a single transistor. And now in the 2015, we are down to sizes of a few nanometers. So the technology we are using right now is the 22 nanometers technology. That's pretty small. How was that possible? Well, first of all, it was rather simple. We had this era of simple scaling. We just made the transistor smaller and smaller by improving our technology. We use lithography for that, and we just improved this technology to make these transistors smaller. We hit a barrier there, so we had to be a little bit more creative with the beginning of the 2000s. Still some scaling, some innovations where we started not only put the transistors on a flat surface, but only started to do some kind of 3D packaging. We used some new materials. But will that continue? Can that continue all the way for more decades to come? Well, as a physicist, for my feeling, there is a physical limit. If you see this y-axis here, I put this number here, 0.1 nanometers. 0.1 nanometers is 1 angstrom. That is basically the size of one single atom. So it's hard to believe that transistors can get any smaller than 1 atom. So physics some kind of dictates the absolute lowest limit that we can reach. So it will be hard to get there, actually. And in fact, there's another thing, even getting there close to this absolutely limit, we will head into some problems, and that problems will come from quantum mechanics. And I'm going to tell you why that is most probably a problem for us. If we look at our technology or our macroscopic world, it is a bit like this highway. Everything works well when everybody stays on their side of the road, I would say. So cars on the right side go in one direction, cars on the left side go in another direction. No problem here, no interference. That changes, or the same is true for microchips. Everything works fine if the electrons stay on the lanes that we gave them. So these tiny copper lanes, if they stay there, no problem. It starts to become a problem if we make the structures smaller. Then we have quantum effects, and this is something that I showed in this small video on the right. This is a simulation of an electron, and it is an electron hitting a wall that the electron cannot pass through. And you see most of the electron, or the probability distribution of the electron is actually reflected just as we would expect it. But on the right side of this wall, of this white line, you see a little shadow. I can hardly see it here, but yeah, if you believe me, there is some whitish shadow going, passing through the wall to the right side. That is what we call quantum tunneling. And if we start, this is a really strange effect. Electrons pass through objects that were planned for us to be a barrier, a barrier that they cannot pass through. That makes building computer chips, of course, a little bit hard if the electrons just start jumping around like we didn't expect it. So the question that is behind my talk here, or behind the science that we are doing, is if we cannot avoid quantum mechanics, and we cannot avoid it if we get smaller and smaller, why don't we use it? And that's the basic idea. So what we want to do is, let's build a quantum computer. And so this is the final moment where you can leave the room if you are scared about my first part. We have to talk about some concepts of quantum mechanics, but very briefly. And then in the second part, we just built one quantum computer. So first of all, some concepts of quantum mechanics that we need to know. Let's take a look at classical physics, or we take a picture, we take classical soccer. This is Manuel Neuer, our goalkeeper. He plays a fairly simple game. No offense taken here. I love him as a player, but the game is fairly easy. He needs two informations to play the game. He needs to know the position of the ball, and he needs to know where the ball is going. That's fairly simple. But that's classical soccer. Now we play quantum soccer, a very small kind of soccer. Here the game gets a little bit more complicated. Manuel Neuer now has to decide what he wants to know. He can know the position of the ball. If he decides that he wants to know where the ball is, he has absolutely no idea where the ball is going. Or he can play it the other way around. He can say, okay, I want to know where the ball is going very exactly, direction and velocity. Then he has absolutely no idea where the ball is. You see, this game is a little bit harder to play. A personal note, maybe I find it a little bit unfair that Manuel Neuer gets very much money for playing this simple game, and me as a physicist, I'm not nearly getting as much money. Thank you. It's actually hard to get a full position at a university here in Germany. But anyway, so getting back more to the physics, this is classical physics. You know the position and the velocity, no problem. And this is quantum physics. You can know the velocity, that's the arrow. Then you have no idea where the particle that we're talking about is. So that is this red blobbish thing that I have written there. Or, like we physicists like it more, we make a diagram. We have this contribution here. X, the x-axis tells you where is the particle, and this W means what is the probability to find the particle at the given position. So it's very likely that it's here. It's not so likely that it's here, but it still can be here. That's basically, that's how we like it even more, to show a little bit off. This is an equation. That's Heisenberg's uncertainty principle. A very simple equation. The precision we know where the particle is, times the precision we know the velocity, or in that case it's the momentum, but for you it's the velocity, is always bigger than this number. This is simply a number. So you cannot know all. And this is an intrinsic principle how our world actually is. It's an intrinsic uncertainty. When you're going to small particles, you cannot know it all. That's really, that contradicts what we see in each day. Our macroscopic world works completely different. But going to small particles, this is how the world works. And from this easy principle, we already can explain us quantum tunneling that I was already talking about. We have this barrier. We have an electron, let's say it's an electron, and this has this distribution. We don't know exactly where it is, or how we physicists like to write it down. And now you can already see there is some probability that the electron is behind the barrier, and that's how quantum tunneling is working. And you have now the understanding how quantum tunneling is actually working. One picture I have to show you because I found it on a that might seem to be a little bit inappropriate now, but I found this picture on a toilet in our university. It's physicist humor, I guess, but you will see what I mean. It's this here. Heisenberg may or may not have been here. That's what physicists laugh about in their breaks. Okay. there is an uncertainty in the position and the velocity of small particles, but that's not only true for positions, velocities, but also for other properties like states, quantum states. That is the concept I want to show you here. We are, in a classical world of computers, we have classical information, classical bits. We can have bits which are turned on or off, 1 or 0. That's not true for quantum bits. We call them qubits. There we have a superposition. We have just the same like in this position and velocity where we are not quite sure in what position we are. The same is true for this quantum state now. We might have a 0, we might have a 1, but we are not quite sure, and that's what we call a superposition. These superpositions are really fickle. If we interact with them or take a close look at them, they break and we have either a 1 or a 0. That's why we have to hide this superposition in a box, and we are not looking inside. When we are looking inside, we are losing the superposition, and we are having either a 1 or a 0. That leads me to the crux of the presentation here. I wanted to flip a coin in front of 100 people, and I'm a bit nervous if I can catch it, but I did it. This here, what I did now, I flipped a coin. This is not a superposition. This state of the coin now is just described by probability. There was a 50-50 chance either to have heads or tails. And my ignorance, because I don't know I haven't looked, so I'm not sure what it is. But of course, the state of the coin is decided. The universe somehow decided either it is heads or tails. That's a complete different kind of randomness when compared to our superposition, because this superposition in our box, nobody decided at this point before we look into the box if we have a 1 or a 0. And that is the power of qubits, because we can use these superposition to do calculations, as I will show you now. But again, this is an intrinsic randomness. It is not because we have not that we physicists are lacking good microscopes to look closer at the particle. It is a real intrinsic randomness. Nobody decided the state of the qubit at this time when it's inside of the box. So what is actually a qubit? How can we get a qubit in real life? Classical bits. We can use another picture for classical bits, these spinning tops, child toys. They can be either up or down, so that would represent our 1 bit or 0 bit. Qubits are a bit. We physicists also say that some of the very small particles, like photons, electrons, they also have a spin. The name is not very good because these particles are not really spinning. But what they have is they have a magnetic field. They have a north pole and a south pole. So if we put now such a particle in a magnetic field, so like in a giant magnetic field, this small tiny electron, for example, with its spin, would flip in a way that the north pole of the particle would face to the south and vice versa. You can imagine that like a small compass needle that you are just bringing into the magnetic field of the Earth. You can open the compass and use a little bit of your energy to turn the magnetic needle, which is your compass, into the other direction. You can force it in the other direction. And we can also do that with our qubits. We can use energy to turn it the other way around. Then you need two information. If you ask me in what state is your qubit, you need two information, two numbers basically. How likely is it that the qubit is facing up, or how likely is it that the qubit is facing down? That doesn't seem very innovational, I would say. But the magic starts when we use more than one qubit. If we have a classical 2-bit system, these are the states that your qubit, sorry, I said qubit. If we have a classical 2-bit system, this system can be in 4 states. It can either be 1, 1, 1, 0, 0, 1, or 0, 0. 4 states, but you only need 2 information to describe this system. You need to tell me what state is the first bit and what state is the second bit. 2 informations. With a qubit system, it's a little bit different. And there is some mathematics behind that, but I want to explain it without any mathematics to you. This qubit system can be in 2 trivial states. Both are facing up, both qubits, or both are facing down. What's really a little bit more complicated are these 2 states. These are states that we call entanglement. One is up, one qubit, and one is down. These qubits are now very free in whatever direction they want to face, but they are absolutely not independent. So if the one spin is up, the other one is down. But beside that, they are really, really free to have whatever position they want to have. And that, you see, that system is way more complicated. You need more information, actually, to describe the system. In that case, you need 4 information, A, B, C, D, to describe completely this system of 2 qubits. And it's getting even more complex when you're using more qubits. This is a comparison of classical information or this quantum bit systems, how complex they are getting. You see very trivial this complexity of a classical system, which is the blue line. But this other, our qubit system, that is really getting complicated. You need a lot of information to describe your entangled qubit system. In fact, so many information that if you have this system here, 300 qubits, you would need more information to describe an entangled system from 300 qubits. You need more information than atoms in the whole universe. It's really complicated. And that is one of the power of this qubit entanglement, because you can describe complex problems, complex systems. One more thing that we need to know about entanglement, and then we're done and we'll start building a computer. If we have an 8-bit register and we want to rewrite the register, we need to rewrite the register step by step. So we rewrite the first bit, then the second bit, the third bit, and so on. That takes time. An entanglement system of qubits is different. If you have this entanglement of 8 qubits and you change the first state, or you measure the first state, the first qubit, all the other qubits will change their state immediately. And that's really powerful, because you could, if you have 2 entangled particles and you have the one here on Earth and the other one on the other side of the universe, if I would measure the one electron, the spin of the one electron, the spin of the other electron, which was a superposition before and not decided, it instantaneously decides its state. So if I measure this electron to be up, for example, this electron will be down instantaneously, despite the fact that it's on the other side of the universe. This is really strange effects that happen with quantum mechanics, and that's why Niels Bohr, this is one of the first scientists who really worked on quantum mechanics, said if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. So that helped me a little bit through the first semesters of my studies of physics. So don't worry, these are just some easy concept, or not really easy concepts, but some concepts that we have understood now, and now we can really start to build a quantum computer. But maybe first the question, I showed you now that quantum computer is really complex. Is it thus faster, more powerful than a classical computer? Well, not really. Maybe it's even slower. because it's such a complicated machine, but the power lies in the fact that it can solve complex problems in less steps. So whenever you have a problem which needs a lot of calculations, a lot of steps to get to the right result, that might be a problem that is made for quantum computers. Just like this problem here. Very trivial problem. You have a traveling salesman, and he needs to visit some cities. He wants to visit all cities, but only once. So every city only once. And he wants to find the shortest route to go or to visit all the cities. That seems to be really an easy problem. It is not, because the number of routes that he can take is vast if you increase the numbers of cities. So that's the equation there up there. The factorial of n minus 1, n is the number of cities, and the big N is then the number of routes he can possibly take. This is the table I made for you. If you have 2 cities, there's only 1 route. That's trivial. If you have 5 cities, there are 24 routes. Oh, okay. 10 cities, 362,000 routes. 28 cities, 1 times 10 to the power of 28,000 routes. Well, it's pretty much, if we take a normal classical computer to calculate all these routes and find the shortest one, so let's take a brute force approach, so we test all the possible routes. For 10 cities, that will take us 0.3 milliseconds. Well, that's pretty okay. I can wait that entering it in my navigation system in my car. 32 years. 28 cities, older than the universe. You cannot solve this problem, which looks so trivial, when the number of cities is increased to such a low number. And that is one of the problems that quantum computers may be may have an advantage, because they can calculate more of this. A classical computer needs to take first route, second route, third route, and calculate every length of it. Quantum computer can make that in parallel. Okay, where is that's sad for the salesman, but where is the larger the larger effect on our society? It's here. Cryptography. Our cryptography is based on this method, I would say. You have 2 prime numbers and you multiply them. That's really easy. Everybody of you could do it with a pocket calculator. But if you do the other way around, if I give you this large number and tell you, please give me the prime numbers that if you multiply them, give this large number, this is really hard. And not only for you, this is also very, very hard for a computer. And that's basically what our encryption system is based on. If you take larger numbers, this is not a really large number, but what usually is taken today is 1024-bit numbers. That takes classical computers thousands of years to decode your password. Quantum computer could do that in minutes. So whoever gets hands on a quantum computers has some advantage in this world. He could read your emails or get your money from your bank accounts. So you see, there is some incentive, I would say, to work on this technology. There are even other for me as a scientist, I'm not so much interested in your bank account, but what I'm interested in is some modeling, really complex modeling of molecules or crystals. That's what I'm interested in. That's also something that quantum computers could do very effectively. I have to tell you about one problem that we have when we now start to build a quantum computer, and that is decoherence. Decoherence is our enemy. Before that, that's a classical computer. If you take a look while it's calculating, if you look inside the computer, there's no problem. He will not take care that you look inside the computer. With this superpositions of qubits, I already told you there's a problem. If you take a look there, if you take a measurement, we have a problem because we lose this superposition. When when we measure the system or take a look into the system, we end up with a single bunch of atoms and electrons and 0 and 1s, just like you. No offense taken here, but also like me, but this is no special computer anymore. So we need to take care that we are not, that the system can calculate by itself and not being disturbed, I would say. There's actually one good thing about that. The NSA will have harder times to decrypt quantum informations because we would at least recognize that that NSA was reading our emails, our quantum crypto, our quantum encoded emails. So what we need is a new concept, and it a bit reminds me of this book here, Douglas Adams. We need a computer which is calculating by itself and just give us the result. And that really sounds strange, and I'm pretty surprised that there are actually quantum algorithms way before physicists start to build quantum computers. There are two algorithms I want to show you. The one is the Shor algorithm. With this algorithm, it is possible to solve this problem that I already showed you. You have two prime numbers, or you have a large integer number, and you want to know the prime numbers. That if you multiply them, give this large integer, and this works in principle. And the other one is a Grover algorithm, is also a problem which is really, it sounds trivial, but it is not. I give you a telephone number, and you have a telephone book, and you want to see which name belongs to this telephone number. That is also a very hard problem for a classical computer, because the only strategy a classical computer can have is start at A and walk down or test all the names and go through the telephone book basically. Quantum computer has an advantage here because he can test more than one name at the same time. So that's Grover algorithm, also theoretically established in 1996. Okay, we have algorithms. So what we really need now is a quantum computer. So we need qubits. I showed you that we need qubits trapped and still detectable. And we need long coherence times because we don't want to lose this superposition state. So we want to have a closed system. So how do we want to do that? There were some approaches, and I briefly touching these. 2001, IBM did a quantum computer with 7 qubits with an NMR computer. I will say something to that later. And they used Shor's algorithm. You remember this code cracking prime number thing. And they were able to find the prime numbers for this integer. Is anybody able to do that here? No? 5 is good, yeah. And 3, yeah. Perfect. Sir, you are a quantum computer, basically. Okay, that doesn't seem to be impressive, but all these strange things I told you about quantum mechanics and those algorithms, these people are calculating with qubits, with superpositions and algorithms we don't understand. That's pretty amazing, although the result is not so impressive. We could have done it, but anyway, the concept works. So I think that is pretty fascinating. There were some more developments with 8 qubits in ion traps, 14 qubits. This 4-qubit system on the bottom solved this equation. I didn't dare to ask that question here. I couldn't solve it by myself. But anyway, there are concepts and realizations of this quantum computing, actually. The one thing that is a little bit, which is what could be a problem, is that these concepts here, NMR computers, ion traps, I'm not explaining it, but they are really complicated. You need to go into vast vacuum chambers because you don't want your electron spins to interact with gas. You need low temperatures, really low at 0 Kelvin. You need laser systems. These are really complicated systems filling up more or less this whole room here. You don't want to have that on your office desk. So bottom line, this is badass science. That costs a lot of money. So material scientists, and there we're coming back to materials, always looked at alternatives, more feasible, more easy ways of realizing a quantum computers. And people were surprised to find it right here, in diamond. Not a perfect diamond, actually, but something, yeah, I like this quote here, it's from a physicist: crystals are like people. It is the defects in them which tend to make them interesting. Yeah, it's when I'm thinking, no, I never learned. I wanted to make a remark about my wife, but I spare that. So we're talking about diamond crystals, but not perfect diamond crystals. We need some defects. These defects, in our case, are an NV center, that is a nitrogen atom, that's where the N is coming from, and a vacancy, a void. And that's here, this is our perfect crystal, but this is a nitrogen atom here, and a void, a vacancy. This NV center has some really interesting properties for us. It is a trap for electrons, and we need the electrons for our quantum bit, because, as I already said, the electron has a spin, it is a qubit for us, and it has a really long coherence time in diamond, because diamond is made out of carbon. These are carbon atoms, they are very light, and the bonding between the atoms is really strong. So the only thing that really could disturb our quantum state in our solid, in our diamond, is vibration of this lattice. So if these carbon atoms would start to vibrate because the temperature is too high, our NV center, our qubit, would be disturbed and we would lose our coherence. But that is not the case for diamond at room temperature, because the bonding is so strong. Basically, the carbon is not vibrating. There are no phonons, that's how we call it. And that's a good thing, because that means the coherence time of a qubit in diamond is rather long. So that's the material we want to work with. But now, the next question is, of course, are we able to detect our qubit in our diamond? Well, yes. What we usually do is we shine light on it, laser light, and what we see then is that a different light comes back, which is what we call photoluminescence. If you take a microscopic image of your surface, these bluish dots there, these are single NV centers. So using a laser, a really simple approach, just shine light on it, you can detect your qubits. That's good. How does it work? Well, we have an electron in a ground state without any additional energy, and now we shine light on it, and that means the electron goes on an excited state. It doesn't want to stay there. Nature likes to be on a ground state. You know that from Sunday afternoons on your couch. You're going back down, but you have this fluorescence light that is coming from this dropping back on the ground level. This is what I showed you on the slide before. Now, we can detect our NV centers, but can we also, and that's essential if we want to build a quantum computer based on this technology, can we also distinguish between spin up and spin down? Well, we can with a little trick. Before we shine our laser light on our electron, we use microwave radiation. Microwave radiation is a tiny bit of energy, and that has one effect. We lift up our, we leave our spin down system and go into something that we call the spin up. So we are basically changing the direction of our little electron compass needle. So now the compass needle is facing up, and now if we now shine light using our lasers on this electron, it goes up in the excited state again, but it drops down on a different way. It now takes an intermediate step and drops back down on the ground level. The special thing about this way back is that there is no detectable light, or at least not so much detectable light. So we now have a system where we can, just with a laser, and a microscope measure if our spin was up and down. And we also can use microwaves to write our qubit and make it spin up or spin down. And what we can even make more is if we time this microwave pulse the right time, so it doesn't make it too long, not too short, then we have an actual superposition. So just by having microwaves, laser, and NV centers in diamond, we have a quantum computer. And actually, a quantum computer that you could, that's really, it would fit on a more or less on an office desk here. But now, of course, the question is, where do we get the diamonds from? We cannot take natural diamonds. This is a nice picture here. This is a diamond mine from 1940. It was closed, but this claimed to be the largest hole excavated by hands. So people really were digging this hole by their hands to get the diamonds out. Kimberley, South Africa, really impressive. We cannot use these diamonds because they're too dirty. Nature is too dirty. So if nature is too dirty, we have to make it by ourselves. And what we do here is we use microwave plasma reactors. That sounds nerdy, so I called it microwave oven. So what we have here is a plasma chamber, microwaves that ignite a plasma. And in that plasma, this is this bluish area here, we take really simple gases, methane, because that's where the carbon for our diamond is supposed to come from, and hydrogen. These gases go into the plasma, and plasma is more or less energy, and we can break these molecules. And so we have some kind of radicals, CH3 radicals, and these radicals want to find new binding partners. And at that moment, we give them a binding partner with a substrate, and on that substrate, these radicals go and form a diamond lattice. Self-organization, we were already talking about that today. Basically, we just turn the right knobs, and this works by itself. And it really works, and I want to show you that by showing you this video here. This is a look inside our plasma chamber. This glowing stuff is our plasma. And we have here diamond substrates, actually. This is 10 millimeters. The thickness is 0.5 millimeter. And now I'm running this video, and you see the diamonds actually growing in our plasma reactors. I hope so. Okay, I have no... Okay. So, unfortunately, in the course of a few days, this is not as fast as you can see it here, these diamonds are growing from 0.5 millimeter to 3 millimeters. They don't look like the diamonds you would give your spouse, your wife, but that's, again, a little personal note, because when you're able to grow diamonds, you want to see if they are shiny as real diamonds that you would buy in a shop. So I went to a jewelry and asked them, could you please polish me this stone, which is not looking like a natural diamond, neither like not looking like a natural diamond. Could you please polish me this diamond as a brilliant? And the guy in that shop was a little bit suspicious and said, okay, what kind of material is that? And I said, that's diamond. Could you polish it, please? And he said, where do you have it from? And I said, I made it by myself. So we had issues, I want to say. But I found somebody who polished me these stones, and they look really beautiful. They're really shiny because they're perfect. There are more or less no inclusions. They're really whitish. I made that once. So don't worry, I'm not using taxpayers' money to grow diamonds, in personal diamonds in my laboratory. We're just doing that on weekends. You were laughing. One thing is missing. We can make diamonds now, which is a nice story for Republica, but for quantum computers, we need one thing is left. We don't want to have the perfect crystal. We want the crystal with the NV centers in it. So where are we getting our nitrogen from, and where are we getting our vacancies from? Two methods that we use. The one is ion implantation. We use an ion gun. we have this really in our laboratories, an ion gun. We are shooting, science is pretty cool. You are using cool stuff. So if you're thinking about science, a career in science, you can shoot with ion guns. We are using these ion guns. We're shooting ions, nitrogen ions, on our perfect diamond crystals. And this is what happens. Those ions are implanted in our perfect diamond crystals. What happens is, obviously, nitrogen is in this crystal, and also some voids, because we made some defects. Then we simply put the diamonds into an oven and do something that we call annealing, 700 degrees. And then, again, self-organization. Again, that's no magic. The holes, the vacancies are moving to the nitrogen. And what we are ending up are the NV centers that we need for our qubits in diamond. This is the one way we do it. The other way we do it is this here. We call it delta doping. We are simply growing diamonds. Just as I have shown you, we take these carbon atoms and we arrange them. And then at one specific point in our growing process, we enter, we put not only methane and hydrogen, as I showed you, into the process, but also for a very short time, nitrogen. So what happens then? We're putting the nitrogen into a small layer of this diamond, and we have something like this. Nitrogen in our diamond crystals. Then we have also electron guns, of course. We're using electron guns to shoot it on the substrates, and by that we are getting again voids, vacancies in our crystal. And then again we make this annealing, and again we have some, or we end up with these NV centers that we need for our quantum computers. So, you made it. We're basically through the talk. I wanted, thanks for staying, very impressive. I wanted to end with a final slide where I showed you that these quantum computers based on diamonds really work. I wanted to show you this year, April 2012, there was a real, people really built something like that, a quantum computer from diamond, two qubit diamond quantum computers. They used the Grover algorithm. This is this database finding your telephone number in a large telephone book. And 95% right answers from the first try. I wanted to show you that, and I wanted to tell you that if I wanted to decode your passwords, your current passwords with such a qubit system, we would use around 4,000 of those qubits. We are a bit far away from that right now, but we are on our way. Don't change your passwords tonight, but maybe think about it in the next couple of years. But there are documents from Edward Snowden that says NSA actually runs a project that they call Penetrating Hard Targets, I like the name, where they invest $80 million US dollars to build a quantum computer. So you see, although those concepts are quite abstract and might seem to be far away, as always in science, those concepts can become true pretty fast. So, okay, I planned that this is the last slide, but then I realized that's not what I wanted to tell you about in my talk. It's not so much about numbers. It's more about a revolution. Up to now, we were building computers by scaling down. So I showed you that we made the transistors always smaller and smaller. Now the concept is a completely different concept. Now we're taking single qubits and making those qubit computers more and more complex. This is a complete new strategy. Before, we call it top-down, starting with a large macroscopic system and make it smaller. Now it's bottom-up. We are taking single qubits and build the systems more and more complex. I wanted this talk is more about that we as a society, we don't want to miss this revolution. We want to take part in that. And that's why it's important that we talk about these concepts and that we give scientists like me money, that we can work on these concepts because of their possible or the potential that they will have on our society. And for me, this presentation is about the beauty of science, because whenever you think that you hit a barrier where you cannot get any better, scientists will find something new, which is even more, in my point of view, beautiful. To increase or to make technology better. One final sentence, this talk is about it almost always pays off to leave the beaten path and going into the wild. Thank you very much.